Right, hello. Good evening, everybody. Right, that's better. Thank you. Good evening and welcome to tonight's evening meeting of a joint meeting between ourselves, the British Tunnel Society, and MinSouth. Tonight, unfortunately, we haven't got our normal recording of the safety items from John Scoley. So if there is a fire alarm, there is not expected to be one, but if there is one, please exit through the various signed areas and congregate round the corner outside the building at Storey's Gate, please. Anything else, we will be notified by members of the ICE, and we will follow whatever instructions they give. So let's move on to tonight's meeting. Tonight's meeting is going to be chaired by Colin Morrish, who is the MinSouth president. So that really concludes my duties for this evening, and I'll pass over to Colin.
Thank you, Rod, for arranging the MinSouth Council room and the room for this meeting. I want to start this meeting today with just a presentation to two long-standing members of the MinSouth Council. One is Alan Stainer, who's retiring at the end of this year. He's got a few more years left. And the other one is Gavin Boyer. If you could come down, I have something to give you. Over here. Yeah. Oh. Thank you. Thank you. Yeah. Thank you.
Thanks for the phone call.
Yeah. Okay, thank you. Now we're going to have the next talk given to us by Clare, Onal. She has nearly 25 years of geotechnical and tunneling experience. She has worked for contractors and consultants and has been lucky to work on some interesting projects, including working on site during the construction of the large caverns for the CMS at CERN over 20 years ago, working in Turkey on the Istanbul water supply project, tunneling under the Bosphorus, working on Crossrail through design and construction stages, and more recently, involvement in several hydro projects, including Tarbella Hydro Scheme in Pakistan and Kidston Pump Storage Scheme, which she's going to talk about today. Please join me in welcoming Clare Onal in her presentation.
Thank you for that introduction. This is Kidston Pump Storage Scheme that I'll be talking about today, and it's a project that we've been involved in the detailed design of. So I'll talk about the introduction and some background of the scheme in general, then an overview of how pumped hydro schemes work, and then move to the underground works because that's why everyone's here. So we'll talk about some interesting, or let's say some unusual aspects of the permanent tunnel and shaft lining. And then because this is intrinsically a sustainable project, just a slide about some of the sustainability aspects. So the project is in, I've got my laser pointer. Yeah, there it is. So the project's in Queensland, in northeastern Australia, and the nearest town is Townsville, which is 70 kilometres away. Andy was saying that's still a 5-hour drive, probably. And the project itself is it's a completed gold mine, so 2 abandoned pits which are now going to be repurposed into a pumped storage hydro scheme that will form the storage part of a clean energy hub with wind farm and solar farms. So this is just a little bit of background on the location. This photograph here shows the Copperfield River, and gold was apparently discovered here in 1907. I think that's when the secret got out. I like to think that people were finding gold before then, but didn't tell anyone. So this shows a picture of some prospectors who've come to make their fortune, and then a small township built up in this area called Kidston. And slowly the gold in the alluvial deposits started to run out, so the excavations started. And that culminates in what you see here, which is the lower pit called the Eldridge pit in Kidston gold mine, and this is it when it's completed. So this gold mine was operating from 1981 until 2001. I tried to find out how much gold they got out of there, and what I found was the ore deposit was in excess of 40 million tons, and the average grade was 1.8 grams per ton. So once they've taken all the gold out, and the pit is abandoned, and now the plan is that this will form part of the pumped hydro scheme, and this will be the lower reservoir. This is a schematic from the Australian Renewable Energy Agency website, and it's just to explain a little bit about how these schemes work in general. So you can only have a pumped hydro scheme in very specific topography. You need a water body at a high elevation and a water body nearby at a lower elevation, so that you get the pressure head. So the flow cycle, starting from this top reservoir, is it in the right place? Yeah. So the water flows down the intake here into the powerhouse, where it's going through the turbines and generating the electricity, and then flows down into the bottom reservoir, and then the cycle is complete. Then this is a bidirectional turbine. So the same water is then pumped back up to the top. And the solar farms and the wind farms and whatever mixed renewables are used to pump this water back up to the top. So because generally solar and wind farms, the energy is intermittent and dependent on the environment. So this is basically the battery that's storing that energy ready for when the peak demand, so that it can be dropped again. On Kidston, there's already a 50 megawatt solar farm operating. There's the pump storage powerhouse, which will be 250 megawatts, so that's the construction's already started. There's another 200 megawatt wind farm in development. Then there's a 270 megawatt second stage solar farm that's in feasibility. So the specific scheme layout at Kidston is slightly different to the general schematic that I showed in the previous slide. Here we have a vertical drop shaft that is using this elevation difference in this pit. So we have the upper pit, which is the wisest pit, which is this area, and this is all forming the top reservoir. Then the intake shafts are here, you can see, yep. And then the water flows down through here to the powerhouse and out into the lower pit, which is this one here. This is the Eldridge pit. And then, so the difference is about 240 meters. Some key parameters of the scheme. We have maximum static pressure at the intake of 274 metres head, and that gives a generation net water head of 223 metres. And we have a reversible Francis turbine. The reason I'm showing this is because it's relevant a little bit later on in the presentation. And just in case anyone hasn't seen one of these before, the water comes in through this spiral casing. It's fed into the runners, which generates the electricity, turning the shaft, and then the water comes out the centre into the draft tube. And I suppose the figure at the bottom there is that it provides a storage capacity to guarantee 143,000 homes with the 8 hours of electricity. So there were a lot of different companies involved in this project, and still are. I've highlighted here the flow of the direct contacts that we were involved with during the design phase that we've done. So Mott MacDonald were working in a design joint venture with GHD, and Andritz provide the hydro equipment details. Then we're working directly for a contractor joint venture of MacDonald and John Holland. And then Genex Power are the overall client. So now we move to the underground part. This view shows a view as if you were underground and looking at the underside of the pit. And all of these structures in here, all of these tunnels and shafts and caverns are new. So we have a main access tunnel running down here, which is 1.5 kilometres, dropping 200 metres at 1 in 7 down to the powerhouse. The intake structures at the top there, and which transfer the water down through the vertical drop shafts, which are 230 metres deep and 4 metre internal diameter. Then the water goes through the pressure tunnels, or the penstocks, which are 30 metres long, and then they reduce in section from 4 metres down to 2.4 metres. The powerhouse is here, and that's housing the turbines, and that is 18 metres wide, 85 metres long, and 45 metres in height, to just give some scale. And then we have the tail race tunnels that convey the water out through the outlet structures here, 330 metres down into the lower pit. So the part of the works that we were involved with are these highlighted in red, which are the 2 intake shafts, the penstocks, these transitions, and then the tail race tunnels. And a decision was made to have twin smaller diameter shafts and tunnels rather than one larger diameter, so that these could be constructed using a raised bore machine. And then you don't need a bifurcation here and here either. And it also gives the future some flexibility or some options. If one unit needs to be closed, then they could close off one unit and have the other one still operating. So the ground conditions at the intake, this shows a plan, and then you can see a relatively small area in plan, but obviously the 230 metre depth that we're interested in. We are in Einsley metamorphics, and the rock type is gneiss. The intact parameters are really good. We have here a borehole which shows fracture frequencies, and you can see most of it have less than 2 fractures per metre, so it's approaching 100% RQD. And 98%, from the ground investigation that was done, 98% of this rock was class 3 or better. And so we were able to base the design on these rock mass parameters with a GSI of 58, which was good. And the ground investigation also found that the permeability of the rock mass was generally quite low, and that's in the order of 10 to the minus 8 meters per second. So this shows a 3D kind of image of the shafts and penstocks, and the penstocks will be constructed first. The outside excavation of the penstocks will be constructed first by drill and blast, and then the raised bore machine will be used for drilling these 230 meter deep shafts. And these are some photos that were taken from another project where Acciona was the contractor, but it's just to show an example. So this is the pilot hole. This is the pilot drill here, the pilot hole being done. And then this one was an inclined shaft, but see the cutter head fixed. And then this photo shows the cutter head being raised and excavating the shaft. And then once the shaft is done, is excavated, the primary lining will be sprayed. And to do the permanent lining, that will be done with a continuous slip form. So there will be a steel shutter that moves continuously up the 230 meters. So the concrete at the base of that slip form will just be cured, maybe 12 hours or something like that. And then as the concrete at the top is being poured, and then that will continuously be raised until the shaft is concreted. So some of the critical checks that we have to do on hydro schemes where we've got underground works are a check for the confinement. So this is to make sure that the in situ stress in the rock mass is greater by a factor at any point where there's an internal pressure. And in situ stress tests were done as part of the GI, and we were able to, I think they were done by overcoring, and we were able to check that against the internal pressure everywhere, and it was okay. The second check is to make sure the distance between any point where you've got a high internal pressure and atmospheric. So I don't know if it's come out very well, but there's a powerhouse here. Honestly. So that's atmospheric pressure in that powerhouse there. And we need to make sure this distance is enough so that we don't get a seepage path which would cause instability and piping at the open face there. And we don't have enough distance. So that's why we need to put the steel lining in. And then the top of that steel lining, the location of that is calculated to the point where you do have just about, you have the limit for the hydraulic gradient that's acceptable. And that's just a plan showing that this was the closest shaft and penstock to the powerhouse, and that's the base of the shaft, and then that's the steel lined penstock there going in. So the purpose of the intake lining is to minimize head losses, because if we had any roughness or obstructions, that would translate into economic loss for the system. So we have 230 meters of concrete lining, and the top 209 meters are with weep holes, which gets rid of the internal and external pressure. It balances the pressure, so we were able to remove the reinforcement in that section. We then have a short part here of concrete lining just to limit the hydraulic gradients just above the top of the steel liner, and then this penstock is steel lined. So for the top 209 meters, where we have the unreinforced, well, it's reinforced with macrosynthetic fibers, but with no bar reinforcement. And what loads are we carrying? Well, we've got ground load, and then we've done a check with the rock wedge loads that might, that's a separate check, so as if it would impact on just one section of the shaft and with nothing else around, so it would be an asymmetric loading on the ring. And then another interesting load there is a localized water pressure. In case we had a fault with some water, a transmissive fault with some water acting on the shaft, we carried out a check that the lining would be able to cope with that. So this is showing the cross section of the shaft with the weep holes there, and it's 250 millimeters thick and is with synthetic fiber reinforced concrete. And these are showing the different arc lengths which the water pressure was applied, the localized pressure. So moving on to the steel lining, the main loading that we had there we have an external water pressure operating which varies along the alignment length. And a check needs to be done because in a maintenance case, this steel liner could be empty, and then it would have the water pressure acting on the outside. So we were able to rationalize, because the water level changes along the alignment, we were able to rationalize it into two parts. So we had a 100-meter head here and 75 meters on this section. Then we have an internal water pressure inside the shaft where we have full supply level, so that 274 meters head down at the MIV, but it's still high all the way in this section. And they have a transient pressure as well to check. I think that was 320 meters head. So as you approach as we're in this area, we are able to use the rock mass to share the load. So the steel lining can use the rock mass stiffness. But as you approach the powerhouse, obviously there's stress relief and some disturbed rock. So that load sharing is reduced in this zone, and then we don't have any load sharing near to the powerhouse. So in this section, it's just the steel lining with the full supply level. So we optimized these loads, and also because the section of the penstock is changing in diameter and is reducing down. And this diagram shows how it was split into sections of different thickness that were required due to different load cases along the penstock. So the thickness ranged from 18.5 millimeters to 26 millimeters, and then that includes a corrosion allowance to cover the life of the project. So I jump over the powerhouse now. Again, it hasn't come out, sorry. Over to the other side. And this is the tail race tunnels. So again, we had a good rock mass here. We're still in the gneiss in this area, but we've got a fault zone here. And this green area here is a breccia, which was weaker, and multiple faults in the end. So we are using slightly worse rock mass parameters for this section. So it's 330 meters long, and you can see that it's inclined upwards. So it actually the water has to be pumped out into the lower pit. And the reason for this is because the turbines that are sitting in here, they have to be submerged. Otherwise, there's a risk of cavitation and pitting of the turbine steel, which would shorten the lifespan a lot. So this is a closer view of the transition area as the tail race comes out of the powerhouse. As the water flows out, it's coming out of the turbine. This is a schematic just to illustrate what's happening in here, because it's hidden by the other structures. As I said, the water goes around the spiral casing, generates the electricity, and then comes out through this draft tube. And you can see that the end of the draft tube is rectangular, but we don't have a rectangular tunnel. We have a horseshoe-shaped tunnel. And what's more, in this area, we have the high head, not as high as the intake, but because you can pump into the lower pit and back out again, you still have a pressure. So in conventional hydros, you wouldn't have a pressure after the powerhouse because it would be released down into the river. But here we've got that head difference. So again, we have to think about the hydraulic gradients, and this area needs to be steel lined. So we've got a rectangle coming in. We need it to be steel lined in here to minimize the hydraulic gradient. And then we've got a horseshoe-shaped tunnel coming out. So this was modeled in Strand, and this is showing the piece, the transition piece. So there are two of these transition pieces that are sitting inside here. So you can see the rectangular draft tube there, I hope. Yeah. And then the horseshoe-shaped tunnel at this end. And then 10 meters was calculated as the hydraulic gradient distance requirement. As a really complex geometry change over a short distance, and it caused some challenges just to model this, to get from this shape to the horseshoe shape of the tunnel. So it was an iterative process also of working out what the thickness needs to be and modeling this piece of steel. So the plate itself is 25 millimeters thick, and then for these corners where the stress was too high, that they're thickened, but locally thickened to 40 millimeters. Then we need stiffeners around to take the external water loads, and as you can see that where the geometry gets more unfavorable, the stiffeners get thicker. And they have webs as well. So the weight of this piece is around 60 tons, and it will have to be taken into place in 3 pieces and then welded in situ on site. And then after it's placed, the mass concrete will be poured around it to stop up the gap between the excavation and this piece of steel. So then, and there are 2 of these. So those detailed design that I've been talking about was done in late summer in 2022, so late summer last year. And the main access tunnel started construction at the beginning of 2022. And here are some photos that we've got of the construction. So we've got primary lining in there and some drilling at the face. And this is showing the portal of the main access tunnel. So construction is due to be finished at the end of 2024 and to start generation in 2025. Here are some more recent pictures that's sent last week. So the main access tunnel is now approaching down towards the powerhouse. You can see the jumbo at the face there. And at the surface, the upper pit, the Wise's pit, is taking shape, and so the intake structures and the vertical shafts will be constructed in this area. And the lower pit, the Eldridge pit, is still full of water and they're in the progress of pumping out a lot of water from that area. And then you can see the main access tunnel portal just there. So finally, we'll talk about the sustainability of the project. So it's repurposing existing infrastructure. So abandoned mine sites normally have sort of quite a hefty cleanup cost, and part of that now is absorbed into making a new way of producing energy and supplying the local area. Pump storage schemes generally have a longer lifespan than conventional battery storage. So we have design life of 50 years on this project. I think somewhere I read that this is the first large-scale off-river solution. So that's reusing the same water up and down through the scheme, which minimizes the environmental impacts on the nearby river systems. And the way that the mixed renewables, because they're so intermittent and unstable and reliant on weather conditions, so this is providing a way to supply a lot of homes at peak demand using that. And then the production will be stabilized over a large area. I should explain this figure here. This is from, again, the Australian Renewable Energies Agency, and a study was done to try to find how many suitable sites there are around Australia, and there were thousands. I think the figure was 20,000. So a tiny percentage of those would need to be developed, and Australia would be well on the way to being self-sufficient with renewable energy. And this is showing the site as it is at the moment with the solar panels in. It's actually advanced a bit from this now. So hopefully this is the first of many pump storage schemes as we move away from fossil fuels. Thank you for listening, and I hope some of it was a little bit interesting, and I'll take any questions.
Hello, does anyone have any questions?
Thank you, Claire, for an excellent presentation. My name is Peter Townsend. I work for MacDonald. And I was just going to ask you about tail race tunnels, the construction. Is that conventional drill and blast, or is it going to be used as a TBM to use that?
No, it's all the tunnels are drill and blast on this project.
Thanks.
Sebastian Kumpfmüller from Dr. Sauer and Partners. I'm also interested in some of the construction elements of the tunnels. So for the penstock tunnel, I think it maybe was shown on one slide, and maybe you could show it again, where the interfaces between the vertical shafts and the penstock tunnels. And you said they're done in drill and blast, but it seemed to me quite a steep curve for drill and blast, and then where
This
the
one?
end.
Maybe.
Yeah.
So the drill and blast will be this.
You created.
This part here, the outside line, and then first of all this will be excavated along as a tunnel and a stub tunnel at the back, so that you could get access for the raised bore machine, and then the raised bore is up there, and then afterwards it's backfilled with mass concrete around the steel once it's been
That answers
placed.
the question. Yeah, thank you.
Dave Hindle, OTB. I noticed that these two reservoirs, look like they've got quite a large catchment, and certainly the lower reservoir is pretty full of the water at the moment. So, how are you going to dispose of excess water that builds up in those two reservoirs? Because if you leave it, it'll just basically fill up to the same level.
Hmm. I don't know the answer to that.
Ah.
Sorry.
I think somebody cunning
Yeah,
must have an answer
they
to
will.
it.
They will know. I can find out for you from
Yeah,
the hydrogeologist team.
Yeah, okay.
It's a good question.
interesting. Then. It's a great idea, that. I asked the author question.
Andrew Smith, I'm retired. My question was a bit similar, really. I didn't know that was going to be asked, but I was going to ask the other way around. What happens if you get too much evaporation? I'm not quite a climatologist, but it can get quite hot there, can't it? So you presumably have to fill it up at some, because you said it's an off-river scheme. So
Yeah.
I
I
just
guess
wondered-
there must be some emergency or access to the river system, but in the general operation, it's off river, and you're right. There must be some way of keeping it topped up.
Hi, Clare.
Hi.
Jessica Serrano, Mott, MacDonald. The last slide on sustainability,
Yeah.
where it powers all the homes, is that one cycle of emptying?
Yeah.
Okay, that's a lot.
Yeah.
Thank you.
How long does it take?
8 hours. I think it's 6 to 8 hours.
Hi, this is Kivan from WSP Mining. My question, it's your eyes
There's
like looking
there's
around.
another microphone going around up there, and I was thinking nobody's talking.
Just a ghost in the room. Kivan from WSP Mining, and my question is, you were really lucky in your site conditions that you had 2 open pits, one higher, one lower.
Yeah.
Have you looked at the viability of other mines and the infrastructure and the potential for having those kinds of situations? I haven't come across many that just...
Yeah, so places where there's been a lot of open pit mining, so that last slide where they've shown that study has been done, oops, that one, and apparently all these red dots are viable schemes.
Oh, wow, it's fantastic.
So it's thousands and thousands of them in
Brilliant.
Australia, and I suppose maybe other countries like South Africa, where you have had traditionally a lot of mining,
Right.
seem to be really perfect for this type of scheme.
And one other question on that, is there potential for combining open pit and underground mining? So you pump
There
from
should be,
underground to
because
open?
all you need is the head difference.
Yeah, exactly.
And if you have that and you have capability
And the
to
storage.
store water,
Yeah.
then any place that has that could potentially be used for pump storage.
Thank you, fascinating work.
Hello, Claire, over here in the middle. I'm Steve Kay from Bechtel. I've got a question. You've shown the final scheme. There must have been some optioneering as you went through. Could you talk about some of the different options and why they were discounted and why that scheme was selected?
I could briefly, but I came on to work on this project once the final scheme was chosen. So, and then I was involved in the detailed design from that phase. But there were, I'm sure, one of the options was, as I discussed, about having a single or twin bores, and then to do with the construction techniques there. Then I'll have to find out about the other options, yeah.
Hello, thank you for your presentation. My question is, well, first of all, my name is Mehdi, I'm for LBA. How much electricity you are supposed to produce? And the other question is, how much electricity do you need to transfer water to the high level?
So this here, so the scheme is at the moment 250 megawatts, and the production is enough to power 143,000 homes for the 8-hour cycle, and then that water can be dropped at peak demand. I don't know if that answers the question.
But you need some energy to transfer. How many percentage of that will be used for?
So you mean how much percentage of the solar and wind farms are
Yes,
required?
so because you produce something, but you consume something. What's
Yeah,
the comparison with them?
I'd need to check again. I don't have that figure in my head, sorry.
Thank you.
I might be able to help with that one, because the guy at the end of this row here probably knows even better than I do, but I think the site efficiency is about 80% on a
Yeah.
storage scheme.
Yeah, it was 80%, yeah.
Yeah,
On this,
so,
yeah.
so you need to add an extra 20% effectively to take the water back up.
I assume the electricity you're buying isn't using some between where it's produced and where you're taking it.
Yeah. Yes, there's no other. They're going to that equation. So hopefully it's cheap or potentially unused electricity. Yes.
Hi, Clare Rose Bechtel. So one question I had was around the environmental risks. Were there any environmental risks that you had to consider as part of the design inherent with the fact that it isn't a previously used mine?
So there was, for us, not really. We had a basically closed loop system where we've got and we're doing the shaft design for the lining. I think because there is the water could be quite corrosive, so that's why we had that corrosion allowance for the steel, and there was a durability report done for that. But are you talking about the wider environmental impacts?
Just as part of the tunnelling work, so
Yeah,
that's really
so it's mainly corrosion.
Corrosion.
Yeah.
Thank you.
Hi Claire, it's Christoph from Mott MacDonald. I was intrigued by the lovely drain shaft with the weep holes. Were there any concerns that these weep holes would not remain operational during the design life of the asset?
Yeah, we did a check to see what happens if a row or two rows get blocked, and so the shaft's able to take that. And then there's the maintenance and the risk residual is that some maintenance might be needed to clear out weep holes that get blocked.
Thank you.
Steve Parker, consultant. On the pumping back, on the question of how efficient you were, do you draw on the electrical supply locally to pump back up, or do you only use what the turbines or the wind turbines and the solar panels generate?
You can do both. So you can, when it's windy and sunny, you're using the renewables, and then if say you don't have those conditions, but you want the reservoir full for the morning, you could draw off on the low demand, so that you've got that ready for the peak demand the next day.
Thank you.
Hi, Claire, Mike Saville, Mott MacDonald.
Hi.
You did the design in the UK. Did you have to design to Australian codes, and how did you get that approved?
Yes, yeah. This is to Australian standards, which we have to learn as part of the design. Approved by it's an Australian project. They're expecting it to be done by Australian codes.
Hello, Claire. Andy Flato from Bar Hill. A question just following up on the weep holes. Obviously, there was a spacing, I think, of 3 meters that I picked up from the drawing. What was the detail behind the shaft lining? Did the weep hole just end there, or was there a sort of layer of, I suppose, drainage or pressure dissipation
Yeah,
medium, for want of a better word. How did that sort of, what was the sort of approach to that and the design of that?
Yeah, the weep holes extend at least, I think it was 500, half a metre into the rock mass, so you have to get that, and then there's a geotextile lining in the weep hole.
It didn't go around the shaft or anywhere, or it wasn't sort of expanded out, it was just a 500 mil?
Yeah, drilled into the rock mass,
okay.
yeah.
And was it aimed at any fissures, or was it just where
they could, as they go down, because it's a raised bore shaft, and I think when they do the spraying they'll have photograph or maybe LiDAR surveys around, and then if they do come across an area with a lot of faults or more discontinuities, they could concentrate maybe more in that area, but generally it's an equal spacing all the way around.
Okay, thank you.
Quick question again. How much gold did they discover during the construction?
Nobody said anything about that. We'll never know.
Our house is 350 metres long. Only 65 on the drawing.
Well, thanks a lot for an excellent presentation, Clare, and for good questions and answering the questions very nicely. Thanks very much, Mott MacDonald, for providing Clare to give this speech, and for providing a bar after this as well. So you can go to. Is there any more announcements? Good.
Yes, there are. There's some slides. I think I'm going to have to get up and click the... Right. As Colin just said, the bar is sponsored by Mott's and the food is sponsored by the BTS. There is limits to both of those. So don't all run out of here yet. Let me get ahead of the queue, please. Ivor, sit back down.
No, easy. I'm slow. Yes. I need a good head start on you, Rod.
Right, future meetings. Next Thursday, February the 16th, the young members of the BTS have a vacuum waterproofing membrane systems evening lecture, 6 o'clock in here. There's another meeting on the Wednesday the 22nd of February, transferable lessons in tunnelling and geotechnical engineering. This is an in-person lecture in Dublin, so for those that happen to fancy a weekend or a week over in Dublin, there's the opportunity. (16th of March, a Thursday again. Young members have a workshop. This is in person at Warwick University. Risk assessment of logistics in TBM tunnel projects. All these can be found on the website and booking arrangements. Next main BTS meeting is the 23rd of March, and that's on geopolymer concrete in tunnelling. The annual BTS Harding Prize, the closing date is tomorrow. We've been advertising it for a while. We've got quite a few applications in. But for anybody that fancies a late night tonight to write their spiel to be able to apply for the prize. Please get busy tonight. Those that fancy that, please don't go to the bar. Our annual dinner, which is very slightly earlier because of the King's coronation, we moved it a week earlier than normal, is on Friday the 28th of April. Bookings are now open, so please, they're going like hotcakes apparently, so please get on and book your table ready for the dinner. We have Kevin Keegan as the speaker this year. And finally, I think this is the last slide, the design and construction course. Bookings will open on Monday. There is an early discount available until the 30th of April. The course is at Warwick. It's 5 days, residential or non-residential, but I do definitely recommend the residential side. 3rd to the 7th of July. It's a very good course. I've been organising it for about the last 10 or 12 years. Mike King's taken over while I'm chair, so please get the bookings. Think of people within your organisations that could benefit from this course. And finally, the BTS can be found at any of these various locations, so please find out about us and look up the next meetings and everything. Okay, thank you very much for attending tonight, and the bar and sausage and chips is now open. And anybody that hasn't signed the attendance register, please can you, because we really do need to understand the numbers with various correspondence that's going on with the ICE at the moment, so please sign up. Thank you.